Hey everyone, my name is Tejas. Aryan and I are presenting our team's project on behalf of our team about anonymous VoIP over Tor using Donar. This presentation is based on the paper Donar, Anonymous VoIP over Tor. Voice, for some context, VoIP has become the standard for global voice communication. However, the existing anonymization networks like Tor face some severe challenges with latency, making it unsuitable for applications of VoIP. So we are trying to say that Donar bridges this gap to provide high quality anonymous VoIP using Tor without modifying the underlying Tor network. So, for some context, let's understand how communication over Tor takes place. Basically, Tor routes the data through a series of relays, creating multi-hop path to anonymize the connection. Data is encrypted in each of these multiple layers before being sent to this through the circuit, as shown in your screen. Each relay removes one layer of encryption to reveal instructions for the next hop. This makes sure that you don't reveal your source or final destination. So now let's coming back to the topic of VoIP over Tor. We would like to enable anonymous and secure VoIP communication and make sure there's reliability in conversation. But implementing VoIP over Tor is a bit challenging because there's high and unpredictable latency. There's low bandwidth availability as Tor needs to prioritize anonymity over throughput, and there's single link dependency because the traditional VoIP or Tor relies on single circuit, and which makes it prone to interruptions if the link performance degrades or fails.
Now, to give a little bit more context about Donar, which was mentioned earlier in the slides, Donar is a user-side proxy designed to enhance a legacy VoIP application by interfacing it with the Tor network. The core idea of it is simple. Donar opens multiple connections and selects the best performing ones to send the data. For optimizations, Donar improves bandwidth by sending duplicate packets, and it uses different links and dynamically switches to the between the optimal links for optimal performance. Overall, these techniques significantly enhance the reliability of data transmission, making VoIP over Tor more practical and efficient. Here we have a visual demonstrating the Donar architecture. We have the caller and callee on the ends. Donar sits in the middle of the respector caller callee and the Tor client and server. Donar leverages multiple parallel TCP links for traffic distribution while providing UTB socket interfaces at both ends, which enables seamless VoIP application integration and improves the reliability without compromising Tor's anonymity guarantees. Here are the key results from the paper. So we have that Donar achieves a latency of under 360 milliseconds with less than 1% frame loss for most 5-minute and 90-minute calls when using the 12 links. And we also noticed that Donar provides latency stability over time with only 4% difference in successful calls. On the right, we can see graphs highlighting Donar consistently performing well across various metrics, both in short and long call durations. To get an idea regarding our implementation, we tested the VoIP applications from the paper using a 16-minute audio file provided by the authors, which we looped for an hour continuously to simulate extended usage. For the environment, the experiments were conducted on an AWS instance. We set up 2 Docker containers acting as a client and server. Importantly, we used the real Tor network for relay nodes without modifying its underlying structure, as Donar is designed to operate directly on top of Tor.
So apart when we're implementing this repository, we faced quite a few challenges. First of all, the repository which was shared by the authors had missing critical files which are required for running the experiments. The README was also very poorly written, and it was incomplete because there were no proper links that led us to the binaries and any other Docker images. So we had to build our own Docker images by changing the Docker file, and there were also some deprecated libraries and dependencies that caused some compatibility when we are trying to replicate this. We also tried contacting the authors, but they didn't reply to us. So we had to change our plan of action and began correcting a little bit of code and try to reproduce the results as much as possible to check the latency and link performance. Now, coming to the key results, one of the results which we produced was the latency distribution. On the left, you can see the histogram that shows the latency distribution from our experimental run with the Donar system. On the right, it's the latency distribution from the one of the original graphs from the Donar paper. The latency distribution reveals that there was an average latency of 235.49 milliseconds, and the systems performed very well with most of the packets falling below 360 milliseconds, which adheres to the VoIP latency requirements. And the variability in Tor's performance kind of like needs for a robust system like Donar, which can dynamically switch between multiple links to maintain low latency and ensure high quality VoIP communication.
This slide highlights key results from our experiments regarding links. On the left, we have the average one-way delay per link measured in milliseconds. We observe variability across the links, with some links performing under 200 milliseconds and others approaching or exceeding 300 milliseconds. This highlights the impact of link-specific conditions such as relay performance and end-to-end latency. On the right, we have link utilization expressed as the percentage of packets relayed through each link. This utilization distribution shows that certain links handled a higher proportion of traffic, reaching nearly 16%, while others carried considerably less. Uh, this next slide highlights key results using the CDF of one-way delays with insights drawn from the data. This plot illustrates the cumulative distribution of delays. So the expected delay was set at 200 milliseconds, which is marked by the green line. The median delay that we observed was at 224 milliseconds, shown by the blue line. And we noticed that the 95th percentiles occur at the 326 milliseconds, indicating the upper limit of most delays. Finally, delays above the set upper limit of 360 milliseconds account for only 2.9% of the data, which is highlighted in the red. In conclusion, our work with the Donar system demonstrated the feasibility of enabling anonymous VoIP calls over the Tor network, as we noticed reasonable VoIP with Tor, great performance, as well as great link utilization. These results underline that the anonymous VoIP is not only possible, but practical, providing a path forward for privacy-preserving communication tools. Here is the references slide, and with that, we conclude our presentation.